So let's start chapter 7. All right, Chemistry 3101, we've made it to chapter 7. So chapter 7 is one of the longer chapters in the book, and it requires an extra lecture. There's over 100 slides in this slide deck, so there's a lot of information in chapter 7. But since I have your attention at the very beginning, I want to show you a couple of things here, a couple of tables that are going to be really pertinent to us um, who are learning the material and studying it. The first table is table 7.1, which goes over leaving groups. And I'm going to lecture on this in a few minutes. But I went over what a good leaving group was with you last class or a couple lectures ago. I said it's the conjugate base of a strong acid. And so you want to make sure that you familiarize yourself with this table and that you're aware of something that's a good leaving group, and that you also want to know what a poor leaving group is. I just want to check all the tables here. There's a couple of tables that I want to make sure that I show you. And again, I don't have my contacts in, so my vision isn't the greatest. So just bear with me as I try to find them. Where are they? Okay, so another table that's going to be really important to you is going to be this one here. Now, I'm not sure exactly which table this is in the book, but this table is going to help you make a decision as to what kind of reaction is going to occur, or what kind of reaction is going to be favored when we look at our starting materials in chapter 7. So this table, I'm going to tell you right away, you pretty much have to memorize this table. Okay, so I'll put a big red star on this table. You've got to memorize this table because it comes up, Avogadro's number of times. And then the other table that you're going to have to memorize is this one here, okay, where it goes over what a strong base, weak nucleophile, strong base, strong nucleophile, weak base, strong nucleophile, and weak base, weak nucleophile. It goes over all these different types of reagents, and what they can do. So to rehash, and I know I'm getting way ahead, but trust me, I've taught the class long enough to know that you want to kind of front load on the things that students really need to concentrate on. So you're going to need this table. This table, I will not give you these. You have to have them in your brain. And then the last one is the one with the leaving groups. The leaving groups, though, my students usually familiarize themselves with that really quickly. They get the hang of this. And there's only a few of them that we see in this class anyway. Just these ones here: iodide, bromide, chloride, a tosylate, which I'll get into in a little bit, and then water. Those are your good leaving groups in Chemistry 3101. Dust your hands off and walk away. That's about it. That's all we look at. We don't look at any other leaving groups besides those. So without further ado, now that you've seen kind of the major tables that you're going to use in this chapter, let's get into it. And one of the things that you have to do at the beginning of this chapter is talk about alkyl halides. So an alkyl halide is when you have an alkyl group and then you have a halogen attached to it. The halogens that we're going to focus on is chlorine, chlorine, bromine, and iodine. We're not really going to talk about fluorine a whole lot. And the reason why is that fluorine is not a good leaving group. Fluorine is the conjugate base of HF, hydrofluoric acid, and hydrofluoric acid is not a strong acid. It's a dangerous acid, but it's not a strong acid. And so before we get into the whole thing about nucleophilic substitution in elimination, probably the first half an hour or so, or maybe even longer than that, we're just going to discuss alkyl halides. What is an alkyl halide? Where do we find them? How do we name them? Right? How do you name an alkyl halide? Because we're going to use them as starting materials in all of these nucleophilic substitution and elimination reactions. So first we kind of discuss the starting materials, then we get into the reaction. So let's start off here with an alkyl halide. And an alkyl halide is a halide that is attached to an sp3 hybridized carbon like this here, okay? So something that looks like this, that's an alkyl halide, and that's going to be a huge focus of for us in this chapter. If you look at these two here, this one is called an aryl halide, so that would be aryl, and this one is a vinyl halide. Those are not alkyl halides, and so we don't really worry about those whatsoever in this class. When you have the halogen attached to an sp2 hybridized carbon, it doesn't react in the same way as it would if it's attached to an sp3 hybridized carbon. And so again, we're interested in alkyl halides, the one in the red box. The other two, we're not even really going to see those in this chapter. They will not be of interest to us. So let's move on from there. And the reason why we have to spend so much time talking about alkyl halides is because they can undergo a whole holy host of substitution reactions when you react them with a nucleophile. And not only substitution, I should say elimination reactions too. So if we look at this first bullet point here, okay, what's being shown here is a substitution reaction. You're substituting the halogen, and remember, X could be chlorine, bromine, or iodine, not fluorine, right? Because fluorine is not a good leaving group. And you just have a nucleophilic attack, okay, and a loss of leaving group occurring simultaneously, and you replace that halogen with your nucleophile. And the nucleophile could be many things, okay? And then if we look at the second reaction down here, this is not a substitution reaction. This is what we call an elimination reaction. Now, if you think about if you eliminate something from your life, you're getting rid of something. And so that's what an elimination reaction is. You can see that we're losing a hydrogen atom, and we're also losing the halogen too. So we're losing the hydrogen and a halogen. So we call that an elimination. And the curved arrows for this, I bet you can see them right away, that what happens is the base is going to abstract this proton. We form a pi bond and we lose our leaving group in this reaction. So again, I'm just kind of front loading here. What we're going to see is a whole plethora of these substitution reactions and a whole other plethora of elimination reactions. And so if you've read chapter 7, you would have seen things like SN1 and SN2. And those are the types of substitution reactions. We look at SN1 and SN2. And also, if you read the book, you would have seen elimination reactions. We learned E1 and E2 reactions. So just to put this bug in your ear, the reaction that's shown on the top, this is an SN2 reaction, and this is an E2 reaction. That's neither here nor there at the moment. We're not there yet, but I just want to put that bug in your ear just so you're not confused if you go back and watch this video or anything. It says at the bottom, what do nucleophiles and bases have in common? Well, they both have a negative charge, they both like protons, so they both have some kind of high region of electron density. That's what nucleophiles and bases have in common. So it says here, when the reagent, like sodium hydroxide, right? If you think about the hydroxide ion, I mean, is that a strong base? Well, heck yeah. You studied it, Avogadro's number of times in General Chemistry 2 and General Chemistry 1. But can it also act as a nucleophile? Oh, yeah, absolutely. It's got a negative charge. And so sometimes you're going to have an alkyl halide like this one, and you're going to get a mixture of elimination products and substitution products. And if you're thinking, oh, sugar, am I going to have to identify both of those? The answer is yes. And that's one of the things that makes the chapter challenging, is that sometimes we get more than one product. Sometimes we might get 3, sometimes we might get 4. We might even get more than that, So, and I'm not saying that to intimidate you. It's more just this can happen, and we will see it happen. And you've got to be able to identify, what's the major product. Okay, and you can see the major product is the elimination product in this case, and the minor product happens to be the substitution product in this case. So another thing I wanted to tell you is it says here in the example above, which compound is the substrate? So what is the substrate? It's a word I'm going to use all the time. When I'm talking about a substrate, I'm talking about the molecule that has the leaving group on it. So this would be our substrate, okay? Or you could just say the starting material. It's not the base or the nucleophile, okay? So it's really just reactant or starting material. We'll put starting material. And we'll put here oftentimes, not always, but often is an alkyl halide. Not every time, but it oftentimes is an alkyl halide. All right, there we go. So you can see that our substrate is reacting with our sodium hydroxide, right? Hydroxide can act as a base or a nucleophile, depending on the situation. And so we get a mixture of products. We get the product of substitution, and we get the product of elimination. We get both. All right, let's move on from there. So it says here, there's 2 main reasons why an alkyl halide can undergo both substitution and elimination. Let's take a look at these very carefully. Number 1, the halogen is electron withdrawing, creating a partial positive charge on the alpha carbon, and thus it renders it susceptible to nucleophilic attack. So if you look at this molecule here, all they're showing you is this is just CH3X, okay? And remember, X can be what? Chlorine, bromine, or iodine, okay? So remember, X is equal to chlorine, bromine, or iodine, one of those, because they're all good leaving groups, right? They're all the conjugate bases of strong acids. What are the conjugate acids? HCl, HBr, and HI. Those are all strong acids. Okay, so what's happening here is that you have a dipole between the carbon and the halogen. The halogen is more electronegative than the carbon. So that makes it partially positive. You see the partial positive charge here. And so your nucleophile can attack that partially positive carbon and cause the leaving group to leave. So not only do you have the carbon with a partial positive charge, check out bullet point number 2. It says the halogen acts as a leaving group. And for the substrate to undergo a substitution or elimination, it's got to possess a good leaving group. So you can imagine that's a segue into what? It's a segue into this table here where we discussed good leaving groups. So a couple of things. First thing is you notice there's a cutoff in the line here, okay, where you go from, well, maybe I'll use a blue pen or something here, where you go from good leaving groups to, I love it, good leaving groups, bad leaving groups, okay? So what makes a good leaving group? Well, I've said this to you many times. It's the conjugate base of a strong acid. So let's take a look at some strong acids. Is HI a strong acid? Heck yeah, it's got a pK of -11. There we go. Is HBr a strong acid? Yes, -9. HCl, yes. This acid here, this is called, you ready? It's got a long name. Toluene sulfonic acid. Okay? Actually, this is para-toluene sulfonic acid. So p-toluene sulfonic acid. Sometimes we just call it PTSA. Okay? It means the exact same thing. It's just an acronym. Organic chemists love acronyms almost as much as people in the military do. So we have para-toluene sulfonic acid. So that's a strong acid. It's got a pK of -3. And then you have the good old hydronium ion. So hydronium ion, which has a pK of -2. And so our cutoff is actually around 0. If you have any acid that has a pK of less than 0, it means it has a it's going to have a good, it's going to possess, the conjugate base will be a good leaving group is what I'm trying to spit out of my mouth here. So you see that these are all the good leaving groups. Iodide's a good leaving group. Bromide, chloride, the conjugate base of para-toluene sulfonic acid. So we would call this para-toluene sulfonate. Okay, you could just call it a sulfonate if you want. And then water is a good leaving group, right? It's the conjugate base of hydronium. Notice that, excuse me, notice that HF is not a strong acid, okay? It is not a strong acid. It is considered a weak acid. And so fluoride is a crappy leaving group, pardon my language, right? Water, its conjugate base is hydroxide. That's not a good leaving group. The conjugate base of an alcohol is an alkoxide. The conjugate base of an amine is an amide, and none of those are good leaving groups. So if you're thinking, you know, really, man, all I got to memorize are these 5, or I just have to know those 5 strong acids, and those are my 5 leaving groups that I'm going to see all the time. Pretty much, those will be the main leaving groups you're going to see in this chapter. We won't go anywhere beyond that, so don't stress about anything else. That's it for our leaving groups in this class. So now we're going to switch gears. So we just finished section 7.1. Now we're into section 7.2, where we're really going to get into the nitty-gritty on the alkyl halides, and we're going to talk about naming them. How do you name an alkyl halide? The good news is this. If you remember how to name an alkane, right? If you remember all your substituents like methyl, ethyl, propyl, isopropyl, butyl, tert-butyl, sec-butyl, isobutyl, they're all going to be back now. And the only thing we're going to do now is we're going to use halogens as substituents sometimes. So if you have a chlorine, right, that becomes a chloro substituent. If you have a bromine, it's a bromo substituent. If you have an iodine, it's an iodo substituent. And if you have a fluorine, it's a fluoro. It's not fluoro, it's fluoro. We're going to maybe see a few alkyl fluorides. We won't use them much, like I said, but you still need to know how to name them. Anyhow, so once you identify all your substituents, then you put a locant for each one. Is it a 3-bromo, a 2-chloro, etc.? Then you put the name you put the name together out in alphabetical order, and the halide group is the key substituent that we're going to name and locate. So here's just some quick examples. You can see the longest carbon chain in this molecule is propane, and so we have a chlorine at carbon number 2. So this is 2-chloropropane. If you look at this one over here, you can see the longest chain is a pentane. So you have 2-bromo, 2-methylpentane. And then this one down here, wow, they even worked a stereocenter in there, right? So this compound is an R compound. And so it's R5-bromo, 2,3,3 trimethylheptane. in that one. So what's the best way to master that? Is going to be to practice it. So we're going to look at some practice in a little bit. But before we get to that, we have to discuss systematic versus common names. Now, both systematic, which is the ones where you just kind of follow the rules of, 2-chloropropane, right? That would be systematic. But common names are also recognized by organic chemists, and they're also recognized by the International Union of Pure and Applied Chemistry, or IUPAC. And so we need to know common names. And I'll level with you, I'll switch back and forth between the two. And it's not because I'm trying to do it to confuse you or bother you. It's just I'm used to it. Okay. It's just part of life as an organic chemist. We kind of switch back and forth. A good example would be this compound here. We call this dichloromethane. That would be the systematic, right? We have the parent, which is methane, and then we have 2 chlorines. But the common name is methylene chloride, and I would say I use both of them, kind of 50-50. Depends on my mood, maybe, or I don't know, or just what comes out of what my brain forces out of my mouth. And so, how do you name something with a common name? The only time you can name an alkyl halide and give it a common name is if you know the alkyl group. If you know the name of the alkyl group, you can do it. Right? You know that if you have 2 carbons like this, you know that's called an ethyl group. And so instead of calling this molecule chloroethane, you can also call it ethyl chloride. So you put the alkyl group first, okay? And then you put the name of the halogen second. So again, both ways are acceptable, but the only time we use common names, hear ye, is when you see an alkyl group that you know already, if it's an alkyl group that you know. So let's see if we can give, I love this, reasonable names. Well, I would say we want to give the correct name for these, but you can see that neither of these molecules have any kind of group. Like we can't give these as a common name. We have to give them um, a full-on systematic treatment. So let's start with the first one. Could anybody tell me how many carbons are in the longest chain here? How many carbons are in the longest chain? It's going to be 4, right? Thanks, Sarah. Absolutely. And the way we're going to number it is like this: 1, 2, 3, 4. So we have a 2-bromo, 2-iodo, 3-methylbutane, right? So let's scribble that down. We've got 2-bromo, 2-iodo, and I'm doing it in alphabetical order here. 3-methylbutane. There we go. And do we have a stereocenter in this molecule? Is there a stereocenter in here? Yes or no? Heck yeah, right? Oh, absolutely. There's a beautiful stereocenter in here, isn't there? You get a couple options because you notice, let me just remove the numbering that I have here. You notice that on the stereocenter that the lowest priority group is going down, right? This is the lowest priority group. It's the methyl group. So you've got 2 options. You can either rotate this bond so that you put the methyl group in the background. So if we did that, and if we put the methyl group, oops, I didn't do that. So if we put the methyl group in the back like this, yeah, that would put the iodine going straight down, and then that would put the bromine here, like this, okay? So then if we try to identify the stereochemistry, we start with 1, and then 2, of course, we go by atomic number here, so 1, 2, 3, like this, and it's going backwards, so that would be an S compound. So it would be S, 2-bromo, 2-iodo, 3-methylbutane. There is another way to do it. There is another way, and this is for, I would say, proceed with caution on this one. But if you're really, really good at visualizing things, you can imagine yourself looking down, right? Looking down this way, and that way your methyl group is going down, right? And what you would see with your eyeball is you would see that you have to go from the iodine to the bromine to this group. So you're kind of going like this and kind of doing it like an oval shape. But anyhow, you're going backwards. And so it would be S. Can anybody see that the way I did it that way by looking down that axis? If you can't do it that way, it's no problem. I mean, either way works. Either way is going to get you the right answer, isn't it? Right? Okay, cool. So either way is totally fine by me. I just want you to have the right answer. All right. What about the next one? The next one, we have a whole holy host of substituents, right? If you look at the longest carbon chain, it has 1, 2, 3, 4, 5, 6 carbons. Now, should we start numbering from the left or from the right? because either way, you've got substituents at carbons 2, 3, 4, and 5. So would I start numbering from the left or from the right in this case? What do you think would be the right answer? What's going to be our tiebreaker here? It's going to be alphabetical order, right? So this would be a methyl group, right? And then over here we have chlorine. Well, C comes before M in the alphabet. And so we're going to start numbering from the right. So we would do something that looks like this. We have 1, 2, 3, 4, 5, 6. So if we have 1, 2, 3, 4, 5, 6, it doesn't matter which way we go. If you were to go 5, 6 down here, you'd still end up with the exact same thing. So we've got a 2,3-dichloro, 4-isopropyl, 5-methyl hexane. So that's quite a bit of stuff here. So we'll write this down. So we've got 2,3-dichloro, 4-isopropyl, 4-isopropyl, 5-methyl hexane. And now we need to designate the stereochemistry of carbons 2 and 3. So it's 2 something, 3 something. So we need to figure out what the 2 something is. So let's zoom in here. Let's evaluate the stereochemistry of carbon number 2. Keep in mind we've got a hydrogen going in the back. So this is going to be number 4. This is going to be number 1. This will be 3. This will be 2. So we go 1, 2, 3. So that's 2R. So we'll scribble that in here, 2R. And let's do the other one. So let me just remove that. So we've got our hydrogen going in the back. That's going to be group number 4. This is group number 1. This is group number 2. This is group number 3. So we go 1, 2, 3. So that's clockwise as well. So it's 2R, 3R, 2,3-dichloro, 4-isopropyl, 5-methyl hexane. All right. Give me a thumbs up if you're with me on that one. Any questions about naming that compound? Okay. Let's keep going from there. There's no questions on that one. We'll keep on moving. And a little bit more about the structure of an alkyl halide and how we use Greek letters. So when we have an alkyl halide, the carbon that is attached directly to the halogen, we call that the alpha carbon. Okay, so the carbon again attached directly to the halogen, that's the alpha carbon, and then from there you go to beta, gamma, delta, etc. So you're going to see me talk about alpha carbons all the time in this class. And you're also going to hear me talk about beta carbons too, because they come up quite a bit in this class, come up all the time in this class, beta carbon this, beta carbon that. So it says here that the amount of branching at the alpha carbon is going to help dictate the reaction mechanism. Is it going to be an E1, E2, SN1, SN2? And there's 3 types of alkyl halides you need to be aware of. The first one is if you have only one group attached to your alpha carbon, we call that a primary alkyl halide. If you have 2 R groups attached to your alpha carbon, we call that a secondary alkyl halide. And if you have 3 R groups, then we call that a tertiary alkyl halide. So primary, secondary, and tertiary. And just to give you a heads up, right, when it comes to SN reactions, a primary alkyl halide is going to react via an SN2, whereas a tertiary is going to react via an SN1. And again, I know I'm getting way ahead of myself, but I want to put this in your mind's eye so that you're not wondering, why do I have to know this? And if you're sitting there going, well, what's going to happen with the secondary? Is it going to be 50-50? No, not necessarily. And that's something that we're going to look at in the near future. All right, so it's just hang tight and we'll get into that. It says here that some alkyl halides have been used as insecticides. For the insecticides below, label each halogen as being primary, secondary, or tertiary. For the circled atoms, label all the alpha, beta, gamma, and delta. So if we look at this first one here, you would consider this to be primary because the alpha carbon is only attached to one carbon atom. So technically that would be a primary alkyl halide, okay? And we labeled an alpha carbon, and of course this would be a beta carbon, right? This would be a beta, this would be a gamma, this would be a gamma, right? This is a gamma. Nope, that's delta. It looks more like a, this would be a gamma, this would be a gamma, et cetera, et cetera. How would you, oops. I deleted everything on that. Okay, I didn't lose my notes there. All right, so how would you identify this chlorine here? Would you call this primary, or secondary, or tertiary? Would anybody identify this chlorine as being primary, or the? It's a secondary alkyl halide, isn't it, right? Because if you look at the alpha carbon, it's attached to two beta carbons here, and so this is a secondary alkyl halide. So secondary alkyl halide. All right, that's enough. So of course we could label the gamma carbons here. So I'm gonna keep doing that. Gamma carbon here and here, and then this would be a delta carbon. All right. So uses of organohalides. There are many uses for organohalides. Like I said, they can be used as insecticides, and they're used in dyes and drugs in lots of different places. Our book gives quite a bit of interesting background and details on alkyl halides that I'm not going to go into right now. What I would like to do is to take a short break now, and for everybody to try these nomenclature problems, and then we could come back and take a quick look at them.